introduce our first guest speaker for today, Jeremy Howard. Jeremy comes from Fast.ai, and he's also involved with the University of San Francisco and founder of many startups. And so we're very excited to have you here, Jeremy.
Thanks so much. It's a great pleasure to be here. I'm also involved with Doc.ai and Platform.ai. Today I'll be particularly focusing on research and results from Fast.ai and Platform.ai. How many people here have used a Fast.ai course or library or research? Most of you. Okay, so I won't take time with this. So basically, Fast.ai has various online courses. We do research, particularly into how to use less resources to get cutting-edge results. So we got state-of-the-art results in text classification and in training ImageNet networks. And most of the results we show actually use a single GPU, generally not running for more than overnight. The ImageNet results were on AWS Cloud running for 18 minutes at a cost of $40, for instance. Our software, everything we provide is totally free, no ads. It's not a great business model, but so be it. So our software is something that's designed to make kind of cutting-edge results easier to use and get people started with deep learning and also to support researchers. So anyway, if you're interested in any of those things, you can grab them from our website. I want to talk about something which is about humans a little bit. So let me ask you, how many people here have been involved in some way with studying how machines learn, so studying machine learning? How many people? Everybody. Okay. How many people here have spent some time studying the theory around how humans learn? So studying human learning. Very few. Okay. So that's what I expected. It's a pretty normal answer to that question. But I think this represents a problem because humans are an important part of the loop when we're building predictive models or creating things that are going to take actions. So I want to try and convince you that you should be thinking about humans. And specifically, humans do some things better than computers. In fact, humans have about 100 trillion synaptic connections, which is a lot bigger than any machines we have today, even when you network them all together. Brains run very, very slowly, but we have a massive amount of interconnect and really great software, as Peter mentioned. Machines do some things better. Machines run very, very, very quickly and remember things really well. And so right now, there are lots of things that humans do better than computers and lots of things that computers do better than humans. So why would you focus on solving a problem with just one of those things? How do we use them together? For example, if you're interested in computer vision, then maybe you should be studying human vision. There's decades of research around what humans are good at seeing. So for example, are we better at seeing color? Can you see which thing is different in this picture? Or are we better at seeing shape? Can you see which thing is different in this picture? Obviously, we're better at seeing color. It's much harder to see that there's a red circle here. Are we better at seeing orientation, or length, or closure, or size, or what? Right? So if you're studying vision, you need to know the answers to these questions about how human vision works so that you can incorporate human vision into your solutions. If you're interested in this topic, and I hope you should be, then you should check out things like 39 studies about human perception in 30 minutes, which would be a great way to get started on the massive research literature into this topic. Or this fantastic book, Data Visualization, A Practical Introduction. But there are many. But the important thing to recognize is the question of what are humans good at is one that is very widely studied in every field around things that humans do, such as looking at things. And so all of the work that you've done on how do we get computers to look at things, there's at least an equal amount of work on how do humans look at things. So this is interesting to me because I think the answer to this or the kind of the result of this, the implication here of there are some things humans are better at, there are some things computers are better at, is that this whole field of auto ML, which Peter was briefly referring to, and it is indeed rapidly moving along, I think that field has got it totally wrong. Why would we try to automate ML rather than instead figure out how to do augmented ML? In other words, why are we trying to figure out how to get the best results we can with no humans at all? Because we have humans, right? Why don't we figure out how to get the best results we can with humans and computers working together? And it turns out when you combine humans and computers together, you can get much better results than you can with AutoML. And even as AutoML improves, that plus humans plus things that combine the two together optimally is always going to beat just using computers up until the point where computers are better at everything. And that's going to be a long way away. There's no particular sign it's going to happen in my lifetime. I don't know if and when it will happen, but not for a long time. Okay? So this is why I think this is something that we should be studying. So we built a thing. We built a thing because we wanted to see what would be possible if we took one little narrow area and said, let's spend some serious time combining what humans are good at and what computers are good at for one specific topic, which is image classification. Okay, so here's the thing we built. It's called Platform.ai. And let's see what it can do. So what we're going to do is we're going to start with a bunch of hello? Okay, we're going to start with some pictures of cars, which we've uploaded, a few tens of thousands of cars to this Platform.ai system, and it basically lays them out like so. And what we're going to do is we're going to try and create a model of cars based on which direction are the cars pointing. And so you can see in the system we can basically zip through various different projections to try and find some where some cars which are pointing in one direction or another direction kind of appear more towards one side or the other in the system. And so a human is very good at rapidly figuring that out. So the human in this case has found, oh, here's a projection where there's some cars which on the whole are generally pointing to the left, right? So we can go through and find those. And so now we've got 34 cars already labeled pointing to the left. Oh, and here's a few that seem to be pointing to the right. We'll just double check. So one of the things that humans are good at is humans are good at rapidly identifying similarities and rapidly identifying differences. So, so we're good at seeing things that are similar. So that's how we can look at a projection and quickly say, oh, there's an area of the projection where things look pretty similar. And then we can zoom into the things that we selected in the projection and quickly find those ones which are different. So by using this insight about human perception, that we're good at finding similarities and differences, is kind of step one to allowing us to augment the computer to allow us to do here some rapid labeling. So now we've quickly labeled some left and right. We can also realize that it seems to be very difficult to find backs. So now we use an extra feature in this system called Find Similar. We clicked 3 backs manually and clicked Find Similar, and it pops up a whole bunch of images that hopefully are similar to those in some way. And so here we're leveraging another insight, which is humans have judgment. Right? So in this case, the human realized, oh, there's a certain type of car I'm not finding very well, so I will specifically ask the computer to do a particular kind of model, which is find things similar to the ones that I've clicked on. And so once we've done that, we can now zip through other projections, and we can again now try and find ones. And so now we're having trouble finding fronts. So we can click on a few fronts and click Find Similar. And it makes sense, right? Fronts and backs do look a bit the same. So this is, was based on a pre-trained ImageNet model, and pre-trained ImageNet models are specifically trained to be position invariant, right? So it's not surprising it would have trouble, right? But so we're giving it a few examples to kind of get started, and we're giving it some hints to get started. So you can see the human and the computer are kind of having a conversation here, right? But because this is a vision model we're trying to build, the conversation we're having is a vision conversation, where we're moving things around and selecting things, right? And then the computer is trying to say, oh, I see what you're doing there. So we've now clicked train, and we've already got a model that's 92% accurate, right? So we started with something with no labels at all, okay? And we're trying to classify 100,000 images, and very quickly, we've managed to find a few, labeled just 100 or so, 120, using this kind of semi-automated system and this dialogue between the computer and the human. And you can see, actually, I'll just go back and show you a step that we kind of quickly flicked over there. You can see that this system has allowed us to go more quickly than we could otherwise. So after training, kind of pre-training in a sense, we actually now get better embeddings. Right? So one of the nice things is now that this next step of labels we can do more quickly. But here's a cool trick. We're having trouble with fronts and backs still, so we can click front and click back, and then say find a projection that maximizes the difference between those two classes. Right? So again, we're kind of, our part of the dialogue here is to say, oh, we're having a lot of trouble finding the difference between fronts and backs, so please, computer, find a projection that maximizes that difference. Right? So this is kind of how this system works. Here's another example if we were working with faces, right? It turns out that we were trying to separate female faces and male faces. Again, ImageNet's not particularly designed to do that, but when we put it into the system, it turns out the first projection it came up with was already pretty good at separating out men's faces and women's faces. So we could select a whole lot at once, and we can go through and say, okay, they're all women, after double checking that they were right. And then we can kind of grab a whole bunch more and say, these all look like they're men. So you can see, again, we're using our, they look similar perceptual competency, and then we can zip through and do the which ones look different perceptual competency to find the ones that actually aren't men. And so we can very quickly label this data set by men versus women. And so once we've done that, we can then have a look at some other projections to see what else is going on in this data set. And so one of the nice things about this kind of visual approach is it actually lets you find kind of things that might be wrong or things that stand out. And in this case, this bunch popped up, and we're like, oh, there's actually other ways we could categorize this. So this kind of conversation allows us to actually identify, oh, here are people with sunglasses. Oh, I wasn't originally going to label sunglasses, but now I think about it, that's an interesting category to create as well. So with this kind of dialogue, we can do that. And then so when we train the model, again, it's going to give us projections that are now a lot stronger than the initial ones, and we can now train the next set of labels much more quickly. And look at that. You can see it's like really separated out the two groups incredibly well now, right? And so now if we say try and find a projection that separates men and women as much as possible, then it's going to do a really fantastic job. So we can first of all quickly label a few more. And since it's already such a good model, it's basically got nearly everything kind of nicely separated for us. So we can very quickly add a whole bunch more labels. And then we can grab it on the other side, and hopefully we'll find that they're largely women. And we can go through and quickly check, and it's like, oh, yep, they are pretty much all women. So now suddenly we've labeled 400 of each. And then we can say, separate men and women, and you can see, oh, it's actually pulled them totally apart. So the idea of this is kind of to say, what happens when you spend a bit of time seriously studying what humans are good at and what computers are good at, and then try to create a system that explicitly brings those two things together, right? So it's kind of like a different way of thinking about things. So I want to talk more about this idea of kind of augmented machine learning, but instead of talking about training one particular kind of model, which is computer vision classification models, I want to talk about ways in which data scientists can work with computers to train models more generally. And most of the research I'm going to be showing here actually came out of something called Fellowship.ai, so thank you for the Fellowship.ai fellows. This is a program where folks who generally have PhDs or strong numeric or technical competencies from other fields who want to get into deep learning can do a fellowship through this program. and generally it's to do some kind of research program. And so this is an example of a research from some of the fellows optimizing hyperparameters for image data sets in Fast.ai. The starting point, basically the idea is to say, instead of using 100x compute or 1000x compute or whatever that Kwok-Lee slide that Peter Abil just showed was, what if we use 1x compute and 1.1x human? Right? So, maybe I don't want to pay Google for 1,000 times more compute, and instead I'd like to spend an extra 3 minutes of my own time trying to figure out a good set of hyperparameters. So anybody who's done the Fast.ai course already knows this picture very well, which is how do you set a learning rate? Well, rather than trying 1,000 different learning rates and training a model for that time and giving Google $5,000 for the, for that compute that you just spent, why don't I do 100 mini batches, takes about 45 seconds, and gradually increasing the learning rate, and seeing, so as I gradually increase the learning rate, see what happens to the loss. Okay, so this takes generally less than a minute, and you can immediately find the part where the slope is as strong as possible. Now here's a really simple, so this came from a researcher called Leslie Smith from the Naval Research Lab. The learning rate finder is a very simple but effective approach of finding learning rates. It takes you an extra 1 minute of your time, but avoids the 1000x compute. So you can do this on your own GPU at home. So in this research from Fellowship.ai fellows, they basically said, like, how many things can we just quickly jump to, right? How much real kind of massive hyperparameter search do we need to do? And so they tried various things for these different important hyperparameters. And they tried it on a variety of different vision data sets. And these ones varied a lot, and we specifically measured them according to, because we wanted to do transfer learning, and we said, what if we started with ImageNet? So we actually created this metric, which is the cosine proximity between the penultimate layer activations of a pre-trained ImageNet network, right, based on these different data sets. So we can actually say how similar is each of these to the data set that was trained on the model that we pre-trained. And so you can see, for example, the draw data set was not very similar at all, but the Dodo data set was pretty similar. This is not Dodo as in the game, this is Dodo as in a, I think it's like a home internals photos or something like that. So here's the result. When you look at lots of different possible hyperparameters that you can tune and lots of different possible values you can set them to across all of these different data sets, this one here is basically all of the defaults that you get out of Fast.ai plus the learning rate finder at the place where that slope is as steep as possible. And then red represents things being much worse. So this is like a totally different learning rate for the different data sets. And green represents things being much better. You can see that basically there's almost no spots which are significantly better than the defaults that you get out of the box with the Fast.ai software. You can get an extra 1.7% on one particular data set if you use one particular learning rate. But other than that, there's not even an opportunity to get an extra 1% out of this. So all of this discussion about massive grid searches and stuff like that is kind of ignoring the fact that we actually now know a really good set of defaults that just work nearly all of the time for transfer learning, right? And generally speaking, you want to use transfer learning. It's very rare that you would want to start with random weights, right? somebody must have trained a model that's at least vaguely similar to what you want. And in this case, vaguely similar is not that similar at all. Like these are pictures of medical images in the cancer data set, or pictures of Amazon rainforest, right? They're not at all similar to the pre-trained network we started with. So actually, you can train really good models, really reliably, basically without doing any special grid search or hyperparameter tuning or whatever. Right? So to give you a sense of where that kind of takes you, we show this basic approach in week 1 of a class where the people who take it have at least a year of coding background, but not necessarily any ML background at all. And after week 1, we say, hey, here's a forum thread. Tell us what you did this week. And so far, that forum thread has 1,067 replies. And people basically pop up and say, oh, I live in Trinidad and Tobago, and I built a classifier for masqueraders versus islanders, and I built one for cucumbers versus zucchinis, and I built one for figuring out what city a satellite image is of, and I built one for figuring out which kinds of buses they are in Panama City, and I built one for figuring out different types of batik cloth. And nearly all the time, the responses are, I got approximately 100% accuracy on a held-out validation set. Generally speaking, nearly every student that does this after week 1 says the thing I tried worked basically perfectly with 100 images or 200 images. Right? So the kind of researchers like to focus on what doesn't work yet, which is very sensible, right? Because they're researchers, right? They want to say, oh, here's something that doesn't work. Let's figure out how to make it work. But our research is very much about like, well, what does work yet? And actually, a lot of things work just without much trouble. Okay. More examples. We built something to find from satellite images houses in a state of disrepair. And to give a sense of how good these models are, it's not at all unusual for people after week 1 of this course to say, oh, I discovered that the thing I was looking at, somebody did some academic research on this in the last couple of years, and I've discovered I have a new state of the art. So one student checked it out and was like, oh, I have a new state of the art on accuracy of Devonagari text classification. Oh, I just checked this out looking at spectrograms for environmental sound classification, and oh, it turns out that I easily beat the state of the art on that. This person improved the baseline from the software they used for tune normal sequencing by 600%. This is something that their lab was paying for. So like this kind of thing of like, hey, just use some defaults, do some basic transfer learning, use some simple human augmented techniques like the learning rate finder, will very often give you extremely good results. There are other things you can tune. If you've got a particularly small data set, you might want to do some data augmentation. So does that mean you need to go through all these different data augmentation parameters like Google did with their auto-augment paper, where they spent, again, I think they spent like millions of dollars of compute time to check this out. Well, again, it turns out actually with a bit of simple common sense, you can do it extremely quickly. And specifically, you can do something that we call TTA search. TTA stands for test time augmentation. And that refers to the idea that at inference time, you can try a few different augmentations of these types, right? And you kind of randomly change your image, augment your image at inference time like 5 times, and you average the predictions, right? And it turns out that if you pre-train a model just a little bit, and then you compare just using TTA, different augmentation approaches, so like not retraining the model at all, just trying TTA with different augmentation approaches, the thing you get back tells you the very nearly optimal training time augmentation as well. So if you use this TTA search approach, then basically on these data sets out of the 1, 2, 3, 4, 5, 6 different data sets we looked at, one of them basically wasn't any better, it was neither better nor worse. One of them was a bit worse, and the reason that Sci-Fi 10 was worse was because the researchers in this case forgot to add the particular kinds of augmentation that you'd actually need for Sci-Fi 10, which is to add a bit of padding and to do some random cropping. But all the other ones, they got quite a significant improvement by using this approach. So again, it's like, it's not a lot of compute at all. It's just taking some simple little shortcuts, right? So when you put these simple little shortcuts together, another group of the Fellowship.ai fellows tried using that on the Food 101 data set, and they found they got a new state-of-the-art result. Now, this is interesting because this data set's actually pretty widely studied. And in fact, the previous state-of-the-art result for top 1 accuracy was an ensemble network that was specifically designed to be good at food. Right? Now, in this case, the approach that they used took half the amount of time to train, right? Didn't have any data set specific architecture or design or training or anything, and it was a little bit better then the state-of-the-art in top 1, and a little bit worse on top 5. And one of the things they did here was that at inference time they actually used TTA, which can really help a lot. It's one of these kind of underutilized little tricks. Another thing that they did to make this much faster, so compared to the previous state-of-the-art, not only did they do half as many epochs, but it was also much faster because they used something called progressive resizing. For those of you that followed our speed records on ImageNet training, you might have seen that we use that as well. Another really simple, really obvious idea, which is if you're training for 90 epochs and you're looking at 224 by 224 pixel images, why always look at 224 by 224 pixel images? Why not start at 64 by 64 pixel images? Because they're so much faster, right? And then like train most of it at 64 by 64 and then do a little bit 128, a little bit at 192, and just do the last few epochs at 224 by 224. So when you do it that way, you'll find it can be like 4 or 5 times faster, and you get better results. The reason you get better results is that you've kind of introduced a new kind of data augmentation. Right? It's very hard to overfit when you're literally changing the size of the image that you put in. Right? So like progressive resizing is another of these like simple little tricks you can do to get these kind of state-of-the-art results using a single GPU training for like an hour or so. So basically, they describe the training procedure in this blog post. These are all blog posts from the Platform.ai blog. But basically, what they're saying is we just use the same approach that Fast.ai Lesson 1 shows. And the reason for that is everybody, before they do the fellowship program, takes the Fast.ai course. So they kind of just use that simple technique. There was another interesting example, which is some of the fellows looked at fashion classification. And fashion classification is another area that is massively studied. It's a very lucrative area. Pretty much every fashion retailer has fashion-specific convolutional neural network models. Again, in this case, the fellows outperformed the previous state-of-the-art approaches, and they even outperformed humans. And in fact, on some classes, they even outperformed what they call savvy humans, which is like fashion specialists. So they actually compared the results to people that were specialized at fashion classification. And again, I kind of think in terms of things that do work, you can actually go a long way with simple heat maps, right? So when they looked at the heat maps for their fashion model and said like which bits of the input are they actually looking at, they found, yeah, the models are actually looking at exactly the appropriate areas. And we find this in medical imaging as well all the time. And I mentioned this one partly because like heat maps is such an incredibly easy thing to create. There have been so many people in the research community recently saying like, oh, they're not all that. And again, like there are some specific particular cases, if you look really carefully, where it doesn't work so well. But most of the time, like in the real world, in practical problems, I've never had a problem with heat maps. They've always worked great. Also in the kind of like how to train things quickly and cheaply, everybody needs to know about one cycle. So one cycle is another great technique from Leslie Smith, where on the left here, this is a plot over batches of learning rate, and on the right is a plot over batches of momentum. The basic idea is that you should warm up very slowly. Spend about 30% of your epochs in the learning rate warm-up and about 70% on the cooldown. And then for your momentum, do the exact opposite. So when the learning rate's really high, the momentum should be really low, and vice versa. Right, this makes sense, because at the start, you've got all these random weights. It's really hard to get started. If you've ever tried to train neural networks really fast, you'll have noticed that at the start, it's really easy for the weights and the gradients to kind of zip off to infinity or to 0. So the trick is, start your learning rate really low, but with your momentum really high, for those parts of the weight space where it has found a kind of a reasonable region with kind of consistent gradients, it'll get faster and faster, which is what you want. And for those parts of the, for those activations that haven't found a nice part of the weight space, they'll just slowly bump around trying to find something better. This works really, really well. And you can train things, 3 or 4 times faster if you use this approach. And interestingly, before Leslie Smith created this approach, she actually wrote a paper on something he called the superconvergence phenomenon. And basically, he realized that there were certain kinds of models and certain kind of situations where he could make the learning rate 10 times higher than anybody had trained before, and train them as a result up to 10 times faster. But he had no idea why it was happening, and so he kind of published this paper saying, like, here's an experiment that I did, and there's this weird result, and I don't know what's going on. Can anybody help me? I want to point out that in most sciences, this is how things work. An experimentalist says, I did an experiment. I did this thing in the Large Hadron Collider, and this is the result that came out. I don't know what's going on. And then all the theoreticians study the experimentalists' experiments a lot, and then they say, oh, here's what I think is going on. Here's some experiments you could run. Unfortunately, in the deep learning community, that doesn't happen. Right? It's really, really rare to do what Leslie did and publish a paper saying, here's an experiment for which we don't have a theoretical answer. And it's unheard of, to my knowledge, for theoreticians to actually look at experimental results and try and figure out what's going on. So nobody has yet actually studied, as far as I know, superconvergence. Luckily, Leslie Smith studied it a bit himself and figured out that this is how you can reliably get superconvergence. But I feel like for those of you that are interested in research, one of the big opportunities, I think, is to follow closely experimental results and become a top experimentalist with the goal of then studying theory to figure out why surprising experiments happen. If you're interested in this, I have a long list of experimental results which are entirely unexplainable at this point, and if we could explain them, then we could train neural networks a lot better. Another thing for how do we get neural networks to train reliably and quickly? When you start a neural network, particularly if you're doing transfer learning, some of your layers have random weights, and some of your layers have good weights, right? So you should always train the random weights more. And there are 2 ways to train the random weights more. One is that when you start fine-tuning a network, freeze all of the layers that are fine-tuned, that are pre-trained, and only train the random weights. The other is to use a different learning rate for different layers, so that the layers earlier on in the network have lower learning rates, and the ones later on in the network have higher learning rates. Both of these are going to result in the later layers getting trained more. If you do this, these are some of the tricks that get you these reliably good results, really, really good results quickly. The other thing I'll mention is in the academic research community, vanishingly few researchers know how to train neural nets properly like this. So in general, if you come across a paper that says X doesn't work, particularly if X is anything in the field of transfer learning, take that with a very strong pinch of salt, because it's very, very likely that that researcher just didn't know how to make it work. On the other hand, if you see something that says that X does work, then that's reliable, right? They've definitely gotten it to work. So there's been a lot of examples of papers in the last few years I've seen where people say, here's a thing that doesn't work, and we've checked it, and it just turns out they weren't training their networks properly. So be cautious of that. You may think RNNs are different, but actually the basic tricks that work for computer vision and convnets also work for RNNs. So we actually did a big research study. This is actually done by Sylvain Guger, who's our research scientist. And he discovered that basically the same basic approach works for every data set we tried it on. And that is to use AtomW. So another thing you might have read is Atom doesn't work very well. It actually does work very well. The problem is that most people did weight decay wrong. As you might be aware, there's two ways you can do weight decay. One is to do true weight decay, which is where you actually subtract out when you do the weight update, you actually subtract out a little bit of the weights as well. The other way you can do it is by adding L2 regularization to the loss function. In theory, both of those two things are the same. In practice, they're not, because you also have things like momentum and the Adam gradient squared divisor in there. So Frank Carter and some of his team put out a paper a year or two ago pointing this out, and pointing out that if you actually do weight decay correctly, then you get fantastically good results. And this is called Adam W. Or in the new paper, they've just changed its name to decoupled weight decay. There is one trick to be aware of, and this paper just came out in the last 3 or 4 days, which is that if you're training for a lot of epochs with Adam, the last few epochs tend to go pretty badly. And so there's a little trick you need to do. And in the paper, the trick they suggested that you should do is to clip the gradients so that you don't make the gradients too high. Basically, what can happen with Adam is that because you're dividing by the moving average of the gradient squared, that thing you're dividing by could be a really small number, right? And so therefore, you could get some really big gradients. And they discovered that there are data sets where that can happen. So you can either clip the gradients, or something I've been talking about for a while is you can actually take that epsilon parameter in Adam and gradually increase that. You can anneal that upwards. I don't think anybody's published this yet, but it is actually something that's kind of mentioned in the TensorFlow documentation, which is that when they were training the inception network at Google, they noticed that they could use Adam if they set epsilon to some reasonably big number. So if you haven't come across epsilon before, there's a good reason for that, which is in the original Adam paper, they said epsilon is a number that you should set really small, like 1e neg 8, to basically avoid numerical instability. But when you actually look at the Adam equation, it can do more than that. If you set epsilon to like 1, then that basically means that a really small gradient squared number can never cause the gradients to blow out, right? So these are two ways you can basically avoid this problem. And so with these two tricks, which is basically Adam W plus either clipping gradients or increasing EPS, you can get networks to train very, very quickly and as accurately as with non-Adam approaches. OK, so anyway, if any of those things sound interesting, you should come along to our next course at the University of San Francisco, where we're going to be doing a deep dive into research level questions, such as the kind of research questions that come out of this, as well as doing a deep dive into some of the engineering approaches you can use to try to solve these problems. And OK, that's it. So I think I've got 5 minutes for questions, if anybody has any questions.
One of the problems that neural network has the number of input features that you can consider. And usually in computer vision, people resize their images to the ImageNet like original
224, yeah.
And then train the network. So is there any solution that we can consider having adaptive input for the neural network?
Yeah, so the question is, can we handle image sizes other than the original image size that it was trained on in ImageNet or whatever? The answer is yes. It's actually very easy to do. Before the penultimate linear layer of convolutional net is an average pooling layer in pretty much all modern neural nets. And if you have 224 by 224 import, generally the grid size before that is 7 by 7. And so even the default PyTorch models right now, and I don't know if it's still true of TensorFlow, but it was true of TensorFlow for a long time, those models also, they basically have a 7 by 7 average pooling layer there. And that means that that model can't work on different sized inputs. But both Keras and PyTorch have something called a global average pooling layer or an adaptive average pooling layer that says, don't do 7 by 7. Do whatever pooling is necessary to come out with a 1 by 1 result. So like if you use the Fast.ai library, we do that automatically. We convert every model using this approach into something that works on any size input. So the answer is yes, we already have a solution to that, and this is why progressive resizing then works. And actually, if you do progressive resizing when you train the original model, then you actually end up with a model that is much more resilient to different sizes at inference time. So that works as well. And then another thing that we've done is to also handle rectangular-sized inputs. And again, this is something that if you use adaptive average pooling, you can also automatically handle rectangular-sized inputs. And that obviously makes a lot more sense than squishing everything into a square. Any other questions?
I have a question on your experience between TensorFlow and PyTorch. So we have any student that know both, and what's the general thing of those two?
We switched from TensorFlow to PyTorch a year or two ago because at that time PyTorch was just so much easier to work with, particularly for kind of research level stuff. With TensorFlow 2, things are changing a lot. So now TensorFlow has eager mode, which is one of the big differences. For me, I still find TensorFlow is far more awkward to use, and they kind of tend to answer the same question in 7 different ways in different parts of the code base. And so I find, particularly for research, it's pretty hard to work with. But TensorFlow is definitely going in the right direction. But for me, I still prefer using PyTorch because I find I can get more done more quickly, more reliably. But you know, they're catching up. Let's do one more question. Yes?
So your Fast.ai course is, a lot of it takes place in Jupyter notebooks, and you do a lot of the training there. Can you speak a little bit about some of the production, like putting that code into production and how that's worked out for you?
Yeah, sure. So the question is about putting Fast.ai and PyTorch code into production. So we use Jupyter Notebooks a lot because as an interactive prototyping tool, it's great for doing research and development and for learning. You can do a lot of, a lot of your development there, but then at some point you want to take that model and, well, there's a couple of reasons you might move out of the Jupyter Notebook. One is that you might want to kind of just train a much bigger version, and you might want to kind of make sure that it kind of reliably handles computers disappearing and stuff like that, or do some kind of distributed computation. The other is that you eventually want to take a trained model and put it in production. I actually recently created a new project called, I don't have it here, but it's called Fast.ec2, which handles the former piece. It basically lets you train things on AWS instances really easily. So I tend to kind of do most of my work in Jupyter, and then when I want to train a big version of the model, I kind of put it, basically I'll go, export it as a Python script, and then run it through Fast.ec2. And then for production, the vast majority of people I know do production using CPU compute, not GPU compute. Because if you want to do stuff in production with GPU compute, you need to kind of batch up all of the requests that are coming into a large enough batch that the GPU is actually going to handle it well. And so for most situations, it's unlikely that you're going to be at a scale where that's actually going to give you the latency that your users are looking for. So generally, for CPU inference, we see people just creating a normal Flask, or nowadays a Starlet, async endpoint, REST endpoint or whatever, and just using standard web app stuff. That, you can just horizontally scale it really easily. If you're kind of Facebook or Google or something, then you definitely do have the scale to do GPU-based inference, in which case you might want to use some of the kind of Caffe2 Onyx stuff. But I don't personally know of anybody outside those giant companies that are getting value out of that at the moment. Great. Okay, thanks everybody.